Hello, young grasshoppers. I hope everybody's doing well. Today is lesson 6 in exponential and logarithmic functions. So just to recap, last couple of days we've been spending some time understanding log laws. So we've been looking at log laws in the form of how to deal with exponential equations, and then in the form of how to deal with logarithmic equations. Now, what this lesson is, in some respects, it's some puzzles, sorts of puzzly sort of questions. I don't think that's a word, but of how we can handle logs in other types of questions. So it's called logarithm logics, just understanding how to work with logs a little bit more. Okay, so we're gonna figure out a couple things together first. From yesterday, we know that all the laws of logarithms, we know all the laws of logarithms, but there are still a few other useful common logarithms that we should know that aren't on your formula sheet. So we're gonna figure out those guys first. There's 6 of them I wanna talk about. These ones will involve the first 3. Get out your calculator. You can do some mindless button pushing for a second. Pause me, figure out these 6 for me, please. A reminder, if you are a new TI, you can get your log base from going math and going up to. If you are a newer Casio, you have that math button right on your screen. You can press F4 for math, and you'll notice that the log AB is F2. And if you are an older Casio, you can find that log AB button by going Option, and then Calc, which is F4, and then more options, and then F4 for log AB. Okay, pause me, figure that out. Welcome back, and you're gonna tell me that we've got 0, we've got 0, we've got 1, we've got 1, we've got does not exist, and we've got does not exist. Now your calculator may have said error or something to that effect, but essentially we know it doesn't exist. So 3 things I want you to be familiar with here. You can finish my sentence, we can play this little game together. You can humor me. Log base anything of 1 is 0. Yeah. So we say log base a, and then a can mean anything of 1 equals 0. When I have log base 7 of 7 or log base 5 of 5, or we can kind of take that now to log base a of a. So if the base and the thing I'm taking the log of are the same thing, that's always going to equal 1. Now, that guy should make like perfect sense to you if you think about the fact that we've already talked about the change of base identity. The change of base identity said we could write this as log 7 over log 7, and anything divided by itself is 1. So if the base and the thing I'm taking the log of is the same, I will get 1 there. Okay, and then the other guys, I can't take the log of a negative number, so log base a of anything negative will not exist. Okay, don't ever write D and E, I just was out of room on my slide there. Okay, next 3, go ahead, put me on pause for a second and figure these guys out. So we've got 10 exponent log 2 and 10 exponent log 5. Those are the first 2 things that you were looking at. I said those backwards, sorry, because I had something in the way of my slide. So this one equals 5 and this one equals 2. And what I actually want you to notice there is the base of this log is the same as the base of the exponent, and that's the rule we're looking at here. If the base, let me just actually highlight this for you. If the base of the power and the base of the log are the same, I will end up just getting whatever that number is there. Okay. The next guy, log base 2 of 2 is x. Sorry, log base 2 of 2 to the x is x. Now, you couldn't put that in your calculator, but it shouldn't be a huge jump to say that that equals x if you think about just a couple of things. Number 1, we've already talked about the fact that we have a power law that can put that x to the front. So let's just put that bad boy there. And now I'm left with log base 2 of 2. Well, log base 2 of 2, we just found out on the previous slide was 1. So that's x times 1, so that'll just be x. So what we're saying here is when you see something in this form, you know right away that whatever that little exponent's going to be, that's going to be your ultimate answer. And then down here, we have good old radicals. Remember that radicals can be written as fractional exponents. So you want to think about this 2, the root 2 here as 2 to the 1/2. And then the same thing from up here applies. That 1/2 can come to the front, and I'd be left with log base 2 of 2. And then that would just be half. Okay, same thing with the cube root. So our 3 here are a to the log base a of x will always just give me out x. Log base a of a to the x will give me out x. And log base a of the nth root of a, remember the nth root of a can be written as a to the 1 over n, so then that becomes the rule that was just above it there. I'll just end up getting 1 over n. Okay, so you guys try these. Evaluate without a calculator. By the time I've said that, you should already be yelling the answer to the first one. That's obviously going to be 1. This guy, the 4 can come to the front. I'll have 4 times log base 3 of 3, so that will be 4, because it'd be 4 times 1. This guy I know is going to be 6, so I end up with 4 times 6, and that'll be 24. Okay, kind of a fun day today. Okay. Okay, simplify the following. Again then, if we know those rules, kind of the name of our game here is we want to make things friendly. So I'm looking at this and saying, hey, can I write 25 as 5 to the something? Because if I could have 5 to the something, then it looks like some of those rules we saw in the previous slide. And I can, that would be 5 squared. So I can rewrite this as log base 5 of 5 to the 2k. And then that will equal 2k. Same as this, I want to write this as a to the 1/2. So that'll end up being a to the 1/2 to the x, which is a to the x over 2. So overall, I'm just going to get x over 2. Okay, sorry, I'll take that off for you. This guy, we know that's going to be 7. We know that's going to be 3. I end up with 7 plus 3, which is 10. Okay, now we're going to get a little bit more in depth as we go here. Before I can start looking at putting these guys together, I need to bring this up. Okay, so that applies to right here, which means that 4 will apply to the x and it will apply to the y cubed. So this is going to be log of x to the 4, y to the 12, minus, same thing here. So this will be log x to the 4, y to the 12. So I end up with log x to the 4, y to the 12 over log x to the 4, y to, or sorry, log x to the 4, y to the 12 divided by x to the 4, y to the 12. Now there's 2 different ways I could look at this. Number 1, you could have stopped right here once you got these to both say log of x to the 4, y to the 12. Sorry, that's a typo there. That should be a minus sign. See it right here? Okay, I just typed that in wrong. I'll fix that for you. Once you get that to say log x to the 4, y to the 12 minus log x to the 4, y to the 12, you could have just said, hey, that's the same number minus the same number, so that's 0. I took that one step further first because I just wanted to show you the log laws. And I said, hey, when I'm subtracting logs, I can smush that together to be a single log if I divide the things I was taking the log of. So I wrote it as log x to the 4, y to the 12 over x to the 4, y to the 12. Anything divided by itself is 1, so that becomes log 1. But then we've already talked about log 1 today. That would be 0. So either way, you're going to get 0. It doesn't really matter. Okay, let me clear my screen, and we'll start in on this guy. So here I'm adding separate logs together of the same base. So when I add separate logs together, I will multiply the things I'm taking the log of. So this and this are going to have to get multiplied together. Then I subtract this guy, which means this guy has to be divided. Essentially, when you're trying to write these as single logarithms, anything that gets added ends up to be on the top of the fraction, and anything that gets subtracted ends up being on the bottom of the single logarithmic fraction. So when I write it as a single logarithm, I'm going to write it like this. So I've got the 6x cubed times x to the 5, and then it'll be divided by the 2x squared. I'm going to clean this up. 6 over 2 will give me 3, and x to the 5 times x, x to the 3 times x to the 5 is x to the 8 over x to the 2 will give me x to the 6. So final answer, log base b of 3x to the 6. You always want to show the log laws, but then also simplify as much as possible. Okay, so then this guy, again, first thing I would want to do, I can't put these together as a single log with these 2's in the way. So I want to move that 2 up, I want to move that 2 up. So those will be squared. Now, the root of x squared is just going to give me x. Here, I'll end up with 9x to the 4. Now, this is being subtracted, so the 9x to the 4 should end up on the bottom of a fraction. And this is being subtracted, so the x to the 5 should also end up on the bottom of a fraction. So I end up here. I've got this x on top, and then I've got that 9x to the 4 on the bottom, and I've got the x to the 5 on the bottom. Now I just want to clean this up. This would be x over 9x to the 9, but then one of my x's will divide each other out, so I'm left with log of 1 over 9x to the 8. You may think this is a silly thing to say, but just be careful that you actually do have a 1 here. Just because this guy divides out, it doesn't mean you're left with 9x to the 8. That 9x to the 8 is still in the bottom of a fraction, so just be careful of that. I've seen that happen once or twice. Okay. So when simplifying logarithms, make sure the coefficients go into to be exponents first. You can't combine those into single logarithms with those coefficients there. So always bring them up to be exponents and then combine into a single logarithm. Okay, the graph of f of x equals 5 to the x minus 1 is transformed. Sorry, that would be a typo. I will fix that for you. That should say transformed. It does in your book. Transformed to become y equals f to the negative 1 of x. Now you will remember from your first unit that that means we're taking the inverse. So common steps in taking the inverse. First, we want to write that f of x as y. And then we want to switch x and y. And now we want to get y by itself. So in order to get y by itself, I have to get rid of the exponential form. I get rid of the exponential form by switching it to log form. Remember, base becomes the base. Dude that was free should be locked. So the x will now be locked into the log. Dude that was locked, which is the y minus 1, will now be free. So that's going to give me log base 5 of x equals y minus 1. Get y by itself, I just add 1 to both sides. So y will equal log base 5 of x plus 1. Now, that is a function, and because it is a function, then we would write it in function notation. So we'd say, therefore, f to the negative 1 of x equals log base 5 of x plus 1. Now, I also graphed that for you just so that you could see. I'm probably going to do a really, oh, I could do that. Just so that you could see that that is, in fact, a reflection. Hey, that's pretty cool. That is, in fact, a reflection on the line y equals x. I know I sound like a geek right now, but you should be proud of me that I actually decently added in the line y equals x. I'm proud of me. It's all that matters. I'm proud of me and my mother's proud of me. Okay. If log base 3 of 4 equals x, determine an expression for log base 3 of 16 in terms of x. These are fun little games that you play. They make great test questions. They make great diploma questions. And what we're going to do is we need to play with this 16, and we need to say, how can I make that 16 turn into a bunch of 4s? Because if I could make it say log base 3 of 4, every time I see log base 3 of 4, I could replace it with x. So can I make 16 be written as 4 to the something? And of course, the answer to that is yes, it can be 4 squared. So I write log base 3 of 16 as log base 3 of 4 squared. Now, the 2 can come to the front, so that'll be 2 times log base 3 of 4, and we know that log base 3 of 4 is x. So my answer, my expression in terms of x is 2x. Okay, so this one reads, given that log base 3 of a equals 6 and log base 3 of b equals 5, determine the value of log base 3 of 9 times a times b squared. When we have separate things that are being multiplied, we expand that out to be separate addition. So I'm going to write that as log base 3 of 9 plus log base 3 of a plus log base 3 of b squared. Now, I'm going to take each one of those and kind of see what I can do with them. The 9 I can write as 3 squared. Now, why do I want to write that as 3 squared? Remember, I'm trying to make that friendly. If I can make that number and that number be the same thing, then I can do something with that. Over here, this one's actually ready to go. I already know that log base 3 of a is 6. This guy, I'm going to end up with a 2 there, and log base 3 of b is 5. So that's going to end up being 2 times 5. So I changed that to 3 squared. I brought the 2 over. That ends up being 2. That ends up being 6. That ends up being 2 times 5. And so my final answer is 18. Okay, if log base m of a equals 3 and log base m of b equals 4, evaluate log base m of 1 over ab. So same sort of thing. First thing I want you to see is this is division here. So division gets expanded to be subtraction. So I'll write that as log base m of 1 minus log base m of ab. Now, you got to remember that log base m of 1, we've already talked about, that's 0. Now be very careful when you do this. That's great that that's 0, but there's still a negative right in front there, and you need to make sure you don't drop that negative, okay? See that negative there? The other thing we're going to do here is AB is being multiplied, so I'm going to further expand this by changing that to addition. But again, remember that the whole thing is negative, which means when I turn this into addition, when I expand this into 2 different terms, I should probably do it with brackets and have that negative still in the front. So something like that. And then I know that log base m of a is 3 and log base m of b is 4. So I end up with negative 3 plus 4, which is negative 7. Awesome. Okay. If log base a of 8 is 3 and log base 4 of b is 3 over 2, then find the value of log base a of b plus log base b of a to the nearest hundreds. Well, this sounds complicated, but it's really just a couple of small steps you got to do. You got to figure out what a is, you got to figure out what b is, and then we can go and plug that into this and figure out what the answer is. So let's start with figuring out a. I know that log base a of 8 is 3. I'll switch that to exponential form. That tells me 8 equals a to the 3, which tells me a is 2. Yonder, I'll solve for b here. So log base 4 of b is 3 over 2. Switch that to exponential form. 4 to the 3 over 2. Well, remember, over 2 means the square root. So the square root of 4 is 2. 2 cubed is 8. So b is 8. So now I just plug those values in for a and b into this guy. So that's going to give me log base 2 of 8 plus log base 8 of 2. Let's have some fun with this and do this in our head for a second. 8 is 2 cubed. So this whole thing would be 3 because the 3 can come to the front and I'd be left with log base 2 of 2. This guy, if I want that to be a base 8, 8 to the what would give me 2. That's 8 to the 1/3 because the cubed root of 8 is 2. So this becomes 3 plus 1/3. That gives me 10 over 3 because 3 is 9 over 3. Which is fine and dandy. That would be a beautiful exact value answer, but this particular question did actually ask you to round to the nearest hundredth, so that would be 3.33. All right, just when you thought you were done with trig, I will tell you that your diploma loves asking questions that combine trig and logs together. So don't shoot the messenger. We need to find an equivalent expression here. So what pops out at me right away is this sine of 2x. That's a double angle identity. If you remember, if you listened to me during trig at all, you will remember I said you never, ever, ever want to deal with a double angle. You always want to make that substitution to something that's on your formula sheet. There is only one thing for sine of 2x. So I'm going to change sine of 2x right away to 2 sine of x cos of x. Now I see actually, kind of cute, my 2's divide each other out. My sines x's divide each other out. So that's going to leave me with log of 1 over cos. 1 over cos is the same as cos to the -1, and then that -1 can come to the front, which gives me an answer of D. Isn't that fun? Perfect little question. Okay, the function y equals log base 2 of x is, I did it again, sorry. That should say transformed. Wow, I should proofread these before I go to video. But if I proofread them before I go to video, you guys wouldn't have a chance to laugh at my mistakes. So, you know, I'm doing this for you. That should say transformed, not transferred. I'll fix that for you. So the function y equals log base 2 of x is transformed into y equals log base 2 of 32x. Describe the transformation that has occurred in 2 different ways. Now, probably what jumps up at you right away is this is just a b value, right? And so if I have a b value of 32, that's a horizontal stretch of 1 over 32. So most of you, I think, would have been totally comfortable just saying, okay, I know b is 32. I'm going to have a horizontal stretch by a factor of 1 over 32 about the y-axis. Now, if you read the question carefully, though, instead of just focusing on my mistakes and imperfections, you would notice it said do it 2 different ways. So how do I do the other way? Well, let's just play around with this for a second. This is 32 times x. So why don't we expand that to be 2 separate logs? Log base 2 of 32 plus log base 2 of x. Well, now I can pick on log base 2 of 32 because I can write 32 as 2 to the 5. If I write 32 as 2 to the 5, this whole thing just becomes 5, which means I'm now looking at log base 2 of x plus 5. Well, remember, my original function up here was log base 2 of x. So now if I've just said plus 5 on the end of it, that is a vertical translation up 5 units. So that's pretty cool. All right. Oh, sorry, I got to clear my ink. Okay, given that f of x is 3 to the x and g of x is log base 3 of 27x, determine the simplified form of f composed with g of x. So again, here we're combining some things together again, and we're looking at composition of functions, but with respect to exponential and log functions. So a reminder, f composed with g of x means f of g of x. So first thing I have to figure out is, do I know what g of x is? Yes, I do. G of x is log base 3 of 27x. So I replace g of x with log base 3 of 27x. Now, it says f of that. If this said f of 2, you'd go to your f equation, you'd replace x with 2. This says f of log base 3 of 27x, so I go to my f equation, and I replace the x with my new x, which is log base 3 of 27x. So I'm looking at that. Now, before you get freaked out about that, a reminder, the base here and the base here are the same. When that happens, you're just left with what you were taking the log of there. So the answer becomes 27x. But I need to think about restrictions here. Because I was dealing with logs in the first place, let me take your eyes back up here. The restrictions on that guy would have been x is greater than 0. So those restrictions still exist because it's right here. So you would have to say that f composed with g of x is 27x where x is greater than 0. Okay. All right. So that's it for this guy. Just some fun stuff to practice, and it helps you with your understanding of logs. So you're heading up to there. And as always, if you have any questions, you know where to find me. Have a great day, guys.